Hello everyone. If you ever used XGBoost classifier or are planning to use XGBoost classifier, you might have seen that it's one of the very good model. It's a classical model, but it's a very powerful and efficient machine learning algorithm, and often serve as one of the strongest classical baseline in research and in practice as well. Internally, in this classifier, we are training many different weak learners, which are combined intelligently using an ensemble approach. These weak learners are decision trees. Even though each of these decision tree may be not doing a very good job, but when we combine them, they are doing amazingly well. The biggest challenge in such a classifier is that it has a very complex search space. In practice, often you might have seen this simpler code from sklearn where it's very easy to tune and like basic version of this model. You can start by creating train test split of your data set, train the model, fit it, and you get the results. But this, when you fit the model, it has many different hyperparameters which are internally already selected for you. But what if you want to get the best model possible here? And this change may impact like 4 to 5% in accuracy, which in practice is a lot. So how does big companies and software engineers and smart data scientists tune such a model? I'll show you today. First of all, we'll use a library called RMango. RMango was developed by my team when I was working at R Research. You can easily install this library locally or in Jupyter Notebook, as I'm showing here, using pip install instructions. It will take a few seconds to install. Now we are going to use a tuner capability from ARM. And this tuner capability is the one which allows us to define complex search spaces as inputs to the tuner and finding best model out of them. Defining search space is very easy, like you see here. I'm using some SciPy stat to define uniform search spaces like learning rate gamma. I'm giving it large numbers, variation 0 to 1, try to find a value. It's a float number. It has endless possibilities there. Max depth, I'm saying maybe go from 1 to 10. Again, you don't want to overfit the model. So that's why we are giving it a range and let the model find out what is best possible based on the accuracy numbers. Estimators are like the number of ensembles you are going to train. I'm giving it say 1 to 300, try to find the best possible for me. Again, like the booster, there are different possibilities. So this combination of search space has almost endless values because these both are uniform values, which can have infinite between 0 and 1. Let us define this parameter search space. Objective function is the one which we want to optimize. This is our model. So XGBoost will take a particular parameter. It's very similar to earlier example, but now you, instead of directly giving it XGBoost, we also pass the classifier parameters. We are using here the close validation accuracy. We are getting the mean of the results for all and returning that. So we want to find the best classifier possible here. We don't probably want to keep track of the count of time this will be called. We'll see later how you can visualize the results. Here, as a sample data set, I'm using wine, but you can replace it with your data set. A dictionary is the one which is taken by Mango as input, which tells how many times to run. If you don't define it and pass it, Mango internally works on its own very well. But you can pass it like batch sizes, number of iterations, domain sizes to pick from. Domain size internally controls the complexity of the search. A good starting point is something like 5,000, 10,000 in practice, or you can leave it for Mango to choose on its own. Now we are defining the tuner where the parameter has been passed, the objective has been passed, and some configuration which we defined earlier. You can look at the tuner config to see what it has. It will do initially 2 random points, means that these random points also you can override in the dictionary. Initially custom, we have not passed anything. Default is 20 iterations, which we have also passed here, that run it for 20 iterations and show us the best possible results. Optimizer also can be chosen. It internally is chosen Bayesian here. It can also, many other things are possible here. So it's a very well full-fledged system. Let us use it. Also, it'll keep track of how much time it took to find us the best results. And let us run this tuner now. It's going to find us the best possible hyperparameters for the XGBoost classifier. It may take a few minutes to run. So let us wait for the results. As you can see, it also shows that the 10% of it's complete and get the best results around 97% accuracies. Let the model run and let us see. It already has found almost very good results for us. It is going to run for 20 different iterations. While it is running, let me also show you the parameter search space, which we discussed earlier. In this parameter search space, Our goal internally is to find what is the best possible learning rate, what is the best possible gamma, what is the best possible max depth, number of estimators, boosters. If you want to do this manually, you might have to try many different values, maybe do 10 to 15 random trials and pick the best results. Random trials are often not very resource kind of optimal. We want to do minimum trial and get the best possible results. And this is where Mango's capability come into picture, that internal optimizer, the state-of-art Bayesian optimizer, is very good in running many of these evaluations. While it runs, I had already kind of ran earlier. We can see it will find us the best possible hyperparameters, such as best possible booster, what is the best possible gamma value, what is the best possible learning rate here, number of depth, and number of estimators. It is able to achieve around 97% accuracy, 97.77, which is very good for this data set. It shows out how many hyperparameters it tried. It tried 22 different values. So it has not tried like thousands of parameters, only 22 values, and given us very good results. And also it shows us kind of like some of the values it has tried, like we see here, that many different combinations were tried. Also, we can see some of the sample objective functions. There are many parameters which have only 93% accuracies. Some parameters have 96% accuracy. So it has intelligently searched the space and given us 97% accuracies. You can also look into how the objective function value varies as for different hyperparameters. Here we can plot this number, and you can see that the value changes a lot. So depending on which search space of the hyperparameter you are in, your classifier accuracy can be but like 92% to 90, kind of close to 98%. So this variation is like 6%, which impact a lot of applications if you're very careful in tuning the numbers. We can also look into how the max objective varies. So it starts very small, around 90 to 93. But as the Mango works on it, it is able to find us the best possible regions and plateaus there. Finally, you can see all the results which Mango returns once you run it. And you will see that it tries all these 22 different parameters, different results, and finally also give us the surrogate values, which internally it's learning the decision boundaries and so on. These results are for expert users to see what happens, but for most of the users, you can stop here once you get the best possible hyperparameters. Every time you run, the results may vary a little because it's internally doing search capabilities and some part of randomness is involved. For example, in this run, it gives us around 96.36% accuracies. Overall, every time you will end up in a good region, you will not be in 90s, 92, but you will end up very close to the best possible results. I will share the notebook for you to try it on its own. I'll see you in another video.